Okay. We have, we're not going to start up here, we're going to start down here. This is the last thing, and I used this space when I ran out of other space. But the mass, we start with a planet of mass m, a satellite of mass little m, much less than big M, at a distance, some distance from the planet. And that distance is going to be r. I didn't put it into this figure. But we note that the planet exerts a gravitational force F on the satellite. It's also worth understanding that the satellite exerts an equal and opposite force on the planet. The forces exerted are equal. Naturally, a force of whatever magnitude it is has much more effect on a mass little m than it does on the much, much greater mass big M. You're probably not going to be able to measure the influence of the mass little m on the planet. It's going to be undetectable, although it's there, but the force of the mass exerted by the planet on the smaller mass does definitely influence the path of the smaller mass. Now, Newton's law of universal gravitation says that the force is big G, big M, little m over r squared, where G in this case is 6.67 to 3 significant figures times 10 to the negative 11th Newton meter squared per kilogram squared. This is something we can measure in the lab, what's called the Cavendish Experiment. We actually even have a Cavendish apparatus in the lab. Unfortunately, we can't use it because we've got a climate system that keeps air circulating in the lab, and circulating air would get in the way of what we're trying to measure, because what we're trying to measure is very small, very sensitive. Okay, very difficult to measure, but it could be done. Okay, well, the condition for a circular orbit, if this thing's going to orbit the planet in a circle, now if it's going to go in a circle, it has to have a centripetal force pushing it toward the center, otherwise it would go off in a straight line. And the centripetal force is mass times the centripetal acceleration. Centripetal acceleration, as we saw last class, is v squared over r. So the centripetal force is mass times centripetal acceleration, mv squared over r. And where's that centripetal force going to come from? Well, there's nothing else out there to influence this mass, very much at least. So the centripetal force has to come from the gravitational force, which is toward the center of the planet. The gravitational force is therefore centripetal, and for a circular orbit, it's going to have a magnitude that's equal to the magnitude of the centripetal force. So we set the centripetal force equal to the gravitational force. We get this equation. Ask that that be solved for v. Now, everybody, I think, pretty well solved it. Got v equals the square root of big G, big M over r. That's worth knowing, but this is worth being very sure that you know. This condition, this is where the physics is. This is just an algebraic rearrangement. Now, we asked the question, what's the kinetic energy of the mass? And people came up with a pretty set of pretty good answers in this. Kinetic energy is 1/2 mv squared, so we substitute v in here, and we simplify, and we get the expression 1/2 big G big M little m over r. Fairly straightforward. So we have the kinetic energy of a circular orbit. What about the orbital period? Now, the question I asked here was, what's your strategy for calculating the orbital period? Now, being engineering students and being adept with symbols and so forth, everybody wants to give me a formula or a set of symbolic calculations. That's not what I asked. I asked what your strategy is. Then I asked you to use the strategy to do the symbolic calculations. How do you approach the problem? What's the one insight you have to solve this problem? Well, that insight is how long equals how far over how fast. How much time it takes is how far you go divided by how fast you're moving. Very intuitive idea. And then we simply have to look at our expressions for how far and how fast, and we get our expression for how long. How fast? Well, right there it is. We solve for the velocity, and so the speed of the orbit, the how fast is square root of big G big M over r. Just our solution. How far? Got a couple of interesting answers to how far. How far? Well, you're going to go around a circle. How far is the circumference of the circle? The circumference of the circle, it isn't pi r squared, that's the area. It's 2 pi r. Now, one good, insightful response to this question was it's going to be equal to the arc distance that you have here is going to be equal to the radius multiplied by the angle. Okay? And that's extremely important central insight into a lot of things that we're doing right now. And okay, that's great. The radius is just r, and the angle for a complete revolution is 2 pi radians. So you're going to get 2 pi r out of that insight. Again, very good insight. Okay, so now we know how far and how fast. We can easily find how long. Just divide how far by how fast. How long, we call that the period of the orbit, is going to be how far, 2 pi r divided by how fast, square root of big G big M over little r. We simplify that. We're going to take the reciprocal and multiply by the 2 pi r. The reciprocal is going to have a square root of r in the numerator multiplied by the r gives us r to the 3/2. Square root of gm will be in the denominator. And that can be rearranged in a number of different ways. One way is instead of expressing r to the 3/2 in this way is the square root of the cube of r, which would put the r cubed under radical along with the gm in the denominator. 2 pi stays where it is. Some people even wanted to move the 2 pi here. If you square the 2 pi, you get 4 pi squared, and that could go under the radical along with everything else, and that would be another perfectly valid expression of the orbital period. Important idea is the orbital period does go as the 3/2 power of the radius. So if you're comparing the orbital period at different distances, that 3/2 power is the key to your proportionality, because everything else would be the same for orbits at a bunch of different distances. Okay, now, next question I asked was, you got the mass here, and you got the little mass starting here and moving to a bunch of different points. What happens to the force? Well, if your force is this on a mass here, what does your force vector look like at these points? Now, I asked people to do a sketch, and then I asked some questions about the sketch. Right here, you should stop and make this sketch. Now, we're going from r to what I estimated to be 3r. It's not quite that far, but let's pretend that it is. So between distance r and distance 3r, what do the force vectors at these points look like? We'll pick up on that in the next clip.